Hello, my name is Justina Adangai, and with me is Lydia, Rachel, Josh, and Paul. Our topic for the project is conservation of linear momentum, and our problem is looking at the end collision, because linear momentum enables us, equation enables us to find the final velocities of two particles in collision with each other. We have cart 1 and cart 2. Cart 1 coming off a plane and colliding with cart 2. It either experiences an elastic collision where they collide and move apart, or they experience an inelastic or plastic collision where they collide and stay together. Rachel is going to tell us about the calculations.
Hi, I'm Rachel, and I'll be talking about the calculations for my part of the presentation. And first off, we know that our mass 1 is almost a half a kilogram, 0.579 kilograms, and then mass 2 is 1.195, which are from before. And then the cart at velocity 2, which was sitting down at the bottom of the track, we know is 0 meters per second because it is not moving at the beginning. And then when we took our calculations for the inelastic collisions, which is where the cars hit and then they travel together as a one joint car, the velocity initial of the car that was traveling down the hill was 0.594 meters per second. And then once the cars collided and they traveled together, we measured the velocity to be 0.186 meters per second. And then if we work out the calculations, we know that conservation of linear momentum is mass 1 times velocity 1 plus mass 2 times velocity 2 is equal to, if the cars stick together, that is mass 1 plus mass 2 all times the velocity final. So if we plug these numbers in, we get that the first part is equal to 0.329, and the second part is equal to 0.343. And the variation of differences will be explained by Josh later. And then in our elastic collision, where the two cars hit, or they don't hit, the two cars are repelled off of each other, we had the same, with the same masses, and then the same initial velocity for cart 2 at the bottom. The initial velocity of cart 1 is the same, so it's still 0.594 meters per second. And then the velocity of cart 1 at the bottom changed because they didn't stick together and travel together. It was 0.314 meters per second. And then cart 2 was 0.137 meters per second. Now we can take the same idea and plug it into our equation. Mass 1 times velocity 1 plus mass 2 times velocity 2 is equal to, now we have to take both of the masses and velocity separate since they don't combine. We do mass 1 times velocity 1 plus mass 2 times velocity 2. And then we can plug in our numbers, and then we can get them out. So the beginning, we're going to have the same, 0.329 is equal to, and the bottom one is going to be different, 0.579. It's going to be 0.345. So again, these differences in numbers are going to be explained by Josh.
So this is our setup. We have a track which is raised up a certain height so that when you release our first cart, it'll roll down here, have a certain velocity, then it will run into the second cart. We're doing it two ways. One of them has totally inelastic collision. The other one is an elastic collision. We have a photo gate sensor with a picket fence to register the velocity after the collisions. And then we have extra track so that it doesn't like run off into the floor.
Can you?
Hi, I'm Joshua, and I'm going to be talking about some of the discrepancies that we found in our calculations versus the theoretical and what we actually measured to be true. The equation we used originally models the perfectly ideal situation, and what we have in the lab is not the perfectly ideal situation, so we end up with two numbers that aren't actually equal. And some of the losses in energy are due to friction and air resistance. And then we also have experimental error in our measurements. We try to cut these down in the lab as much as possible by using the physics carts that are very low friction, and then also originally we used a stopwatch to time and get an average velocity for the first cart, but then we used the physics photogate scanner, which gives us a more accurate reading. Also, one of the biggest differences and loss in energy, and this is modeling a completely elastic collision, and when our two carts hit, if you could see it in slow motion closer up, they don't actually hit and stay together. The first one kind of bounces back a little bit and you have a little bit of jerk, so a lot of energy is lost and that collision isn't actually perfectly elastic. So that just describes some of the differences we have here.
Okay, my name is Lydia Quano, and I'm here to just summarize or make the conclusion of what we did on our project. So what we did is we find the linear momentum for both elastic and inelastic collision, and like Rachel already explained in calculation, and Joe's also already explaining why we have some differences in the calculation due to some of the maybe momentum loss. But at the end, we conclude that the conservation of linear momentum is actually works, that the initial momentum is equal to the final momentum.